Combining transformations with absolute value functions. Now that you have seen how each transformation is applied separately, consider an equation with multiple transformations. What goes first? Do you have any thoughts? Take a moment to pause this video and think about it, and when you're done, unpause. Well, it really depends on the notation that is being used for the transformations. To combine transformations in the form y equals a times a function of x, and the function of x has b in front of the x minus h, and then plus k at the end. Use the following order. First, do the horizontal shift of h. Then, stretch or shrink horizontally away or towards the y-axis with the factor of 1 over b first. Then, vertically away or towards the x-axis with the factor of a. Then perform reflections about the y-axis and or x-axis. And finally, do the vertical shift of k. You can also think of it as working from the inside out, starting with what is furthest inside of the function or parentheses. Let's see how transformations in this form get executed. Here's an example. The graph of the parent function f of x, which is equal to the absolute value of x, is shown in the coordinate plane to the right. Graph the function g of x, which is equal to 1/2 times the entire absolute value of the quantity 4x plus 2 to get from f of x to g of x. As stated before, the very first step here is to horizontally shift the function based on what appears here. Since we have a plus 2, which is equivalent to minus -2, we're going to shift the graph of this absolute value function 2 units to the left. Next, we're going to look at our b value, again inside the absolute value section of the function, which is 4, and we're going to horizontally shrink the red absolute value function that we had after we horizontally shifted it, and we're going to horizontally shrink it towards the y-axis by the factor of 1/4. Again, remember the key here with b is it's not equal to b for the horizontal stretch or shrink, it's 1 over b. So you got to make sure that you use that reciprocal in order to determine where the function is going. And now the final step is to take care of our a value that is on the outside of the absolute value. And that a value is 1/2 or 5/10. And because that value is between 0 and 1, we're going to vertically shrink our blue function more so towards the x-axis. That brings us to our final green function in the graph. And we did that vertical shrink towards the x-axis by the factor of 5/10, which is equivalent to 1/2. Another form used to combine transformations is y is equal to a times f of, and then in parentheses we have b times the quantity x minus h, and then plus k. Some people will prefer using this method because it gives away the vertex and its x-coordinate right away. Whereas in the first method we showed before, we did the horizontal shift, but then the horizontal stretch or shrink moved that h value. So if you factor b out of both terms inside of the function, then you would end up getting the x-coordinate of your vertex right away. If you prefer or have a function in this form, perform the transformations in the following order. First, do horizontal stretches or shrinks towards or away from the y-axis by the factor 1 over b. Then do the horizontal shift of h. Then do vertical stretches and or shrinks towards or away from the x-axis by the factor a. Then perform the reflections about the y-axis and or x-axis, and finally do the vertical shift of k. Let's see how transformations in this form get executed. We're going to use the same example. The graph of the parent function f of x, which is equal to the absolute value of x, is shown in the coordinate plane. Graph the function g of x, which is equal to 1/2 times the quantity, or the absolute value of the quantity, 4x plus 2, and describe the transformations used to get from f of x to g of x. So if there's a preference to know the vertex right away, like to figure out the final h value of your vertex or the x-coordinate of your vertex, Then factor the b coefficient from both terms, and the key here is from both terms. You have to do it not only from your x term, but also from this plus 2 that's here. So we're going to factor a 4 out of both of these. And when we do that, we're going to still have the 1/2 out in front, but then we have the absolute value of 4 times the quantity of x plus 1/2. Because again, 2 divided by 4 is 1/2. So now that we have g of x in the form of a times the absolute value of 4 in our case, which is our b, times the quantity of x plus 1/2, we're going to horizontally shrink the function towards the y-axis by that factor of 1/4. Again, remember, b is not the exact horizontal stretch or shrink. You have to put 1 over it to determine that factor. So 1 over 4 tells us it's a horizontal shrink by that factor. The next transformation would then be to horizontally shift the function to the left 1/2 unit. Again, the left is because you have the minus negative, so we're going to the left. And then because we factored the 4 out, we're left with 1/2, so that's how far to the left we move it. And the final step, regardless of the form that we had, is still that vertical shrink of the function towards the x-axis by the factor of 1/2. Now this is also because there is no k at the end of our function. If we did have a k value, we would apply that vertical shift as the very, very last step. Let's try another example. In it, we're going to have f of x be equal to the negative absolute value of x minus 2. And then we have plus 4 at the end. Its graph is displayed. The function g is given by g of x is equal to negative f, and then in parentheses x plus 3, and then plus 6 at the very end. The first step that we are going to do is to write a formula for g that does not involve f. The second thing that we are going to do is we are going to carefully sketch a graph of g of x on the grid to the right, and we're going to label at least 3 points on the graph of g. And finally, we are going to describe the transformations that map f of x to g of x. Let's get started. The first step that we are going to complete is to write a formula for g that does not involve f. So we're going to begin by writing f of x is equal to negative, and then we're going to have in brackets this entire function, and then wherever an x occurs, we're going to substitute in an x plus 3, so that's going to go in here. We're going to have this negative out in front of this whole thing, and then we're going to add 6 at the end. So it's going to look something like this when we first set it up. The next step that we can do is remove this set of parentheses, because with addition and subtraction inside of absolute value, you're just going to execute it from left to right. And now we're actually going to do that. We have x plus 3 minus 2. That'll simplify to x plus 1. And the next thing we're going to do is we're going to take this negative 1 that's out in front here, and we're going to distribute it to 2 terms. There's only 2. It's this negative absolute value and then this plus 4. So it's going to then become positive absolute value of x plus 1 minus 4 and then plus 6, and now we can combine the negative 4 and positive 6 together and get plus 2. And that's our final function for g of x. Next, we're going to carefully sketch the graph of g of x on the grid to the right, and we're going to label at least 3 points on the graph of g. Well, we know that g of x is equal to the absolute value of the quantity x plus 1 and then plus 2. That tells us that our vertex, we could also rewrite the inside as x minus negative 1, the vertex is negative 1, 2. So we can graph that point, negative 1, 2, right here, negative 1, 2. Another point that we can easily find is the y-intercept. If we substitute 0 in for x, we'll end up having 0 plus 1, which is 1, its absolute value is 1, and 1 plus 2 is 3. So 0, 3 is going to be another point on this absolute value function. And the final step would be finding a mirror point, because it's going to go up on one side and then it's going to go up on the other. So if we do the y-intercept and then its mirror point, the mirror point is going to be -2, 3. And we can double check that. -2 plus 1 is -1. Its absolute value is 1. And then if we add 2 to that, we get 3. So we have -2, 3 as our mirror point. And now we can graph this function. And we can see that these 3 points, our g of x function goes through them. Now we're at part C. Describe the transformations that map f of x to g of x. Well, the very first transformation that we need to do is the translation 3 units to the left. And that's because we have an x minus -3, or x plus 3. Then, after we shift it to the left 3 units, we don't have any coefficients inside the parentheses, but we do have a negative that is outside of the function. So we are then going to reflect it over the y-axis, over the x-axis. And after we do that, we're going to then vertically shift it up 6 units. And there's our final function, g of x, and how we got from f of x to g of x through the transformations. Here's another example. We're going to let f of x still be equal to the negative absolute value of the quantity x minus 2 and then plus 4. Its graph is displayed. The function g is given by g of x is equal to 2 times f of, and then in parentheses, 3x minus 1. First part that we are going to do is we are going to write a formula for g that does not involve f. Then we are going to carefully sketch the graph of g of x on the grid to the right and label at least 3 points on the graph of g. Finally, we are going to describe the transformations that map f of x to g of x. We're going to begin with part A, where we write a formula for g that does not involve f. So the first thing that we are going to do is we're going to write down the 2, and then we're going to write down our function in brackets, negative absolute value of, and then instead of x, we're going to put in 3x minus 1 in x's place, then the minus 2, finish the absolute value, plus 4, and then close the bracket. So it's going to look something like this. Okay, the next step is that we can actually drop these parentheses, because inside of absolute value we can combine like terms, and those like terms are going to be the -1 and -2. So that's going to be -3 when we combine them together. And now in this step we're going to take this -2 that's out in front and we're going to distribute it to 2 terms. The negative absolute value of the quantity 3x minus 3, and then also to the 4. So when we do that, we'll have -2, still absolute value of the quantity 3x minus 3, and then plus 8 at the end. Now some of you may want to factor out a common 3 inside of the absolute value, and you can absolutely do that. Some of you also may want to stay at this point to help guide you through the transformations. That's okay too. So you could stop here, or you could continue by factoring out the 3 that's in common from both of these terms. And then because it's absolute value, again, only because it's absolute value, we can now take the absolute value of 3 and the absolute value of x minus 1, and then multiply the absolute value of 3 by -2, which would be -6. So some of you may want to stop here, and others may want to stop here. Either answer is perfectly fine. Okay, so we found our g of x function. It can be either of these two answers. G of x is equal to -2 times the absolute value of the quantity 3x minus 3, and then plus 8. Or g of x is equal to -6 times the absolute value of the quantity x minus 1 plus 8. So in both cases, we have to find our vertex. It's easier to find the vertex if you ended up going to the bottom function. This one that we stopped at partially in the middle will help more so with the transformations. But this one tells us the vertex is 1, 8. That's going to be our vertex. So we can plot that point. 1, 8 right here. The next thing that we can find is our y-intercept. If we substitute 0 in for x, 0 minus 1 is negative 1. Absolute value of negative 1 is positive 1. Negative 6 times positive 1 is negative 6, plus 8 is 2. So therefore our y-intercept is 0, 2, right here at this point. And now notice these are only 1 unit apart, and because we have an absolute value function, we need a mirror point on the other side of 1. So if we substitute 2 in here now instead for x, we have 2 minus 1 is 1. Its absolute value is 1. 1 times negative 6 is negative 6, plus 8 is 2. So our mirror point is the point 2, 2. So 2, 2. So our g of x function is going to look something like this. And here we have our 3 points, 1, 8, 2, 2, and 0, 2. Now let's look at part C. Describe the transformations that map f of x to g of x. Well, the first thing that we can see in the parentheses is we have a horizontal shift to the right 1 unit. After that, we are going to horizontally shrink the function towards the y-axis with a factor of 1/3. Remember, that's 1 over b, so the horizontal shrink towards the y-axis with the factor of 1/3. We can see how the vertex moved then from 3, 4 to 1, 4 because of that horizontal shrink. And the last step is going to be a vertical stretch away from the x-axis by the factor of 2. And that's going to pull the function more upright, having that original y-coordinate here of 4 all the way up to 8. Another way that you could describe the transformations that map f of x to g of x would be to make sure that you factor out the b value from the first and second term that's in this set of parentheses. And if you do that, you would still have 2 times f of, and then in parentheses 3 times the quantity x minus 1/3, and there is no plus or minus k outside. If you decided to do this factoring first, then the very first transformation that you would do is that horizontal shrink towards the y-axis by the factor of 1/3. In the graph, it'll look something like this. So you would go from our original vertex of 2, 3 to be at 2, 4 to be at 2/3, comma 4. The next transformation would be a horizontal shift to the right 1/3 units, or 1/3 of a unit. And when we do that, we now end up at the vertex of 1, 4. And still, because the 2 is outside of the function, that transformation has to go last in this case, and that's the vertical stretch away from the x-axis by the factor of 2. So it's going to make the graph much longer, and it stretches further away on both sides of the x-axis.